Okay, I thought this might be worth a short video because we have to solve this problem over and over and over again inside a compiler. And I think, anytime you have recursive data you're trying to consume or deal with. So the issue is that types can contain themselves. And to know a type schema, we need to know the schemas of the types that it contains. And it's actually just not so obvious how to solve this at first. What I used to do was I would, instead of a type actually containing itself, it contained at the location where it contained itself. Test type schema recursive type. So we have our recursive type here. This is the simplest one we can do that's legal, where it's behind a pointer. So really this is just a pointer, but it's a pointer to recursive type. And when we're making this type, we don't know what type, we're not done yet. So we don't have something to put here. So like, what do you even do? Well, I put like a redirect. I had a type called redirect, basically. And it contained another type ID, or it was unresolved. So I would put a redirect unresolved here and use the ID of this definition from the AST. And then I would go back and update all of those unresolved redirects to point to its type ID once I was done defining it and I knew its ID. And if you're not using IDs, that's fine. You can just replace pointer, unique address with ID, and everything kind of works the same. But I use IDs. So type ID is just a 32-bit number. Could be a 64-bit number as well. Might have to be one day. And so the problem here is, that approach is actually not great, I'll go ahead and say, because you have this fake type, redirect, and every bit of code that consumes and works with types has to decide what it's going to do on redirects. Is it going to follow it? And then it still might infinitely recurse, or is it going to stop there? And there were other issues as well. I honestly can't quite remember because it's been over a year and a half since I changed back. But ultimately, I decided to stop doing that and to move the complexity to construction time rather than consumption time. Now, with the asterisk that at consumption time now we still have to guard against recursion. With the old approach, it was kind of easy because you just didn't follow those recursive references and you were kind of done. You didn't have to track where you've been. But I found that it's actually a lot better for everyone who needs to traverse a type to actually just have to explicitly decide what they want to do when they see a type they've already seen. And so it actually feels like, even though it is complexity and it is a bit burdensome to have to track this, it's really not that bad. It's a very simple concept, very easy to see the state, and you end up getting to make good decisions about what to do. So, but the question is, what are we actually going to do if we've already seen this type? So we're deriving the type schema for a recursive type, and we're going to see that we haven't visited it and see that it's not done yet. And then we're going to make it, I'll close it because we know what this is. We don't need this in scope anymore. And so we're going to get to struct, because it's a struct. And we're going to iterate its fields. And then we're going to call this function that's basically going to recurse on the field. And so at this point, we are recursing on ourself, right? F.type ID is the same as type ID. And this will just recurse forever. And I can show you here. We're just going to overflow. So what do? Well, if we've already seen now I need to make sure, are we going to do visited or are we going to do completed? Because what I could do is go ahead, I could reserve a value ID here. And then as long as no one's going to consume that, we might be okay. So let me just check something here. After we register this meta info, so for this recursive case, Right, we don't actually use the schema, so I think this is going to be fine. My solution to this problem, what do we actually return if this type is already visited? And I'm going to do a little bit of surgery here. Yes, so just make sure we're not doing this in any other places. We're going to insert a gap. We're just going to reserve a place for the one we're currently deriving. So, and because we already have this hash map of type IDs to type schema values, which is the work we're doing, we're just going ahead and make the place in the type schema pool. So what we're going to do is it's actually going to be okay. Now, I can't just check if it's in there because I don't know if it's I don't know if it's resolved or not. Is that true? Let's think. So we're going to see recursive type. It's not already done. So what we're going to do is we're going to reserve a place for it. So it'd be like self.type schemas.insert reserved value ID. And that's going to be self.static values. I had added it. Is there a pool? Pool.reserve ID. Now, is this? No, it's not. It's not a struct of arrays. So we're okay. And then now, we're going to keep going. And if anyone now asks for the schema of this type, we're going to give them back that reserved ID. So that'll include our recursive call down below. And then when we return is when we're actually going to resolve it. So we just need to make sure no one uses it. And they won't. Well, we are handing it out. But I think it's going to be okay. So if you wanted to be a bit safer here, we could add a kind of static value that was like unresolved, or we could have a separate data structure tracking these reserved IDs rather than going ahead and actually putting it in the pool. But anyway, let's come down here. And then now where we fulfill, because what we've done this match on type, and we're actually getting this is a static sum. Let's just go ahead and look at it. We've created a value that represents the schema that we want to store, and then we're going to go ahead and add it. But instead of adding it to the pool, what we're going to do is we're going to So because this pool is not just the pool of values, it's got a little bit more going on here, we kind of want to go through this add routine. Looks to be around, an optimization we don't care about for trivial values to keep things smaller in the pool, and then a hashing. So we do a quality-based hashing for all static values. So what we need as a companion to add is going to be a set on a reserved ID. given a static value. And our job is to update hashes. It's kind of to do this. Then there's interesting. So if we continue forward this way, what this function wants to do is it says, hey, make this ID be this value. And that's what we'd like to call from our from the side where we produce the value. But if it's a duplicate, if that value is already in the pool, I think that we have no choice but to go ahead and still make it point to the right value. So we'll have, we don't really want to do this. And we may end up updating our hash to point to our ID, but that should be okay because the values are identical anyway. I need to rethink a little bit of this deduplication and if it's even worth it or necessary in this static value pool. But this should be, I thought, reserve ID, expected ID. I wonder how I'm doing it in types. Reserve, set type. We just do an assignment. It seems fine. Ownership. Okay. So that didn't go quite as smooth as I was hoping when I decided to hit record, but it's still, I mean, I think it's still illustrative. I think it's helpful. So what we've done now, and I'll go ahead and let's just kind of add some noisy logging so we can maybe see this work. Hopefully it will work. Reserving ID for type, for schema of type, reserving value ID, what we'll do, say returning cached value ID. Okay, and then now at the very end we can just go ahead and say that we are resolving reserved value ID for schema of type to I don't really want to print the sum. I'm not calling it yet. So the type schemas. We don't have to do that at all. Set. And we don't have reserved ID, but we will. And this will be reserved value ID as U32. Let's see if I can get lucky with a repeat here. Yeah. Okay. So I didn't have to add a visited array because I kind of already have one, because the compiler is caching the result of this operation in general already. And this needs to be reserved ID. That we can do. So I hope this works. That would be neat. That would make it a nice nice video. Let's try. And our entire test suite passed with a recursive type, with requesting a schema of a recursive type, which was something we hadn't actually supported before. Okay. See how many times we ask for the meta info of string. Okay, so now we're doing recursive type. We just checked this line. This, I guess we can, yeah. I guess we can go ahead and assert that it's a struct. Forgive me the detour. Test type schema. It is a struct. And what do we do? Reserving value ID 1338 for schema of type recursive type. Register type meta info. And then we reserve 1340 for the schema of this type, because this is also a type. Pointer to a recursive type is going to be 1340. And then it looks like when we go to resolve this, right, which is inside of this, we then ask for the schema of recursive type because the pointer branch recurses. And then we return 1338. That's the type that we promised recursive type is going to be. We found it in the lookup. And we made sure that when we return this, no one is using that value. All we do is put the ID into a struct that no one can access until we've resolved it. And then we immediately resolve 1340 star recursive type, and then we've got this value ID in there for the value that this points to. And then we're going to go ahead and resolve 1338 as the type that contains this, a schema that contains this guy's value. And then let's see, here it is for a simple struct. 1349 is going to be the union. And then we already have a value of 168 for I64, F64, and F32. And then we're resolving 1349 to be this union. So I hope that makes sense. I found that the best approach to this problem is to make some sort of a promise. When we start, say this is going to be the ID of the thing I'm currently defining. And if I encounter myself at any point now, recursively, I'm not going to obviously recurse. I'm going to recurse on myself. I'm going to return that ID, even though it isn't valid yet, right? And then we have to have some invariants to make sure that nobody uses it, or we could even set it to like a poisoned value, or set it to the value unresolved, right? That'd be fine. I didn't do that here because I didn't want to add a whole type of static value just called unresolved, but it may be worth the safety in your case. And yeah, so we stop the recursion, we return the promised value. We say, look, recursive type is going to have this value ID. It just doesn't yet. And then that stops the recursion. We can bubble up, and then we can finally resolve. And this works for cycles as well. As long as we maintain everything we've currently visited in some sort of data structure, and make sure that we're populating it and consulting it before we recurse, this works for cycles, not just direct recursion. So yeah, I hope that was helpful. As you can see here, this is a file that's testing this get type schema function. So the schema of array I3210 is an array, right? And then we have some more interesting ones like this sum type is in either, and the payload starts 8 bytes in, and it has 3 variants. The first one, yes. Second, no. The third one, maybe so. And that variant has a payload whose type ID is the same as string. So yeah, this is compile time introspection, but didn't work on recursive stuff until now. I think that's all for this one. Thanks for watching. If you learned something, please consider clicking the like and subscribe button, and I'll see you next time.